Hi, physics. Mr. Janowski here. This is the second part of the chapter 2 slides. So, the do now questions. First thing, what is the symbol for momentum? The symbol for momentum is P with a hat. So, for some reason, P is the symbol for momentum. What is the equation for momentum? P equals mv. So, that is our basic definition of what momentum is. Think of that first when you think of momentum. P equals mv. Third question, what is the name for a change in momentum? This is impulse. So you can say change in momentum, but there's a special word for it. It's impulse. The fourth question, what is the symbol for impulse? The symbol for impulse is J for some reason and not I. That's just the way it is. Fifth question, what are the two equations for that thing being impulse? Well, J equals delta P, which means also that J equals P final minus P initial, and also J is equal to Ft. Impulse is equal to force times time. So those are our two equations for that thing. And the sixth question, after whom are the units of momentum named? Trick question, they're not named after anybody. The units of momentum and also the units of impulse are kilograms meters per second. So impulse is a change in momentum, so therefore it must have the same units as momentum, and those units are kilograms meters per second. So on this idea of impulse, and in particular the idea that J equals Ft, how does impulse relate to force? Well, remember that forces accelerate masses. That is Newton's second law. That's the most important thing you will learn in physics all year. F equals ma. And acceleration is a change in velocity. So if a force, a net force, is going to change your velocity, it is also going to change your momentum because momentum, P equals mv. So if v is changing, momentum is changing. So that is how forces relate to momentum and how they relate to changes in momentum. Forces cause acceleration. Acceleration is a change in velocity. And because velocity is related to momentum, a change in velocity is going to be a change in momentum. So let's look at especially this bottom version of the formula. J is equal to F times T. So when a baseball bat strikes a ball, it's going to change the ball's momentum greatly. So this ball in the picture was going left, and then the bat hits it, and very quickly it starts going right. So it had momentum to the left, and then at the end, it's going to have momentum to the right. So it's got a big change in momentum. So impulse J is very large. Now, the bat and the ball are in contact for a very short duration of time. So remember those videos we watched in the last class and all the high speed photos of, the bat hitting the ball, the golf ball hitting the club face, things like that. The two things aren't in contact for very long. So the question is, what does this tell you about the force F? So let's look at this equation. J is very large because we're undergoing a large change in momentum. T is very small. So what do we know about F? Well, we know that F has to be very large. For this math to work, if the left side is a big number and the right side is F times a small number, well, F has to be a big number for this to work. So this is just kind of a warning that the forces we're going to deal with in this chapter are often going to be much bigger than the forces we dealt with last chapter. So when Alice pulls Billy on the sled, she might be pulling with 150 or 200 newtons or something like that. In this chapter, when we're talking about the force that the bat puts on the ball, just for a millisecond or two, that force is going to be very big. It won't be, a couple hundred newtons. It might be thousands or tens of thousands of newtons, or even more than that. So when you're looking at the forces you get, just expect them to be very big numbers. So here's a still image from National Lampoon's Christmas Vacation. So we've got Clark is going to fall off of a ladder while he's hanging Christmas lights. He's going to land on the ground somehow. He's either going to land on the driveway or he's going to land on the lawn. So the question is, which surface is going to give him the greater impulse? And the answer is neither. It's a tie. Both surfaces will give him the same impulse because his change in momentum is going to be the same. In either case, if he falls from the same height, right before he hits the ground, he's got a certain amount of downwards momentum. And then after he completes his landing, so after he hits the ground and comes to a stop, he's completely run out of momentum. So the change in momentum is the same, therefore the impulse is the same. Now, clearly, If you're going to fall off of a ladder and hit the ground, you would rather land on the lawn than on the driveway. So something is different, and it's not the impulse. The impulse, we just decided, has got to be the same. So what's different in this situation? The answer is going to be the force is going to be different. So, well, the amount of time it takes, look at J equals Ft, the amount of time it takes is going to be different. And if J is the same, well, that means the F is going to be different. Ultimately, it's the force F that's going to matter. So I just, did some numbers. Let's say that Clark is 80 kilograms in mass. He's going to fall from about 4 meters high. And right before he hits the ground, he's going 9 meters per second downwards. So if we want to figure out his initial momentum, which is to say his momentum right before he hits the ground, these are the numbers you would plug in. P initial equals m times v initial. So that's 80 kilograms times negative 9 meters per second because, he's going down, so it's a negative velocity. So do the math, and you end up with P initial. So the initial momentum is negative 720 kilograms meters per second. So what will his final momentum be after he comes to a rest? Well, his final momentum is going to be 0. His final velocity is 0. So P sub F, P final, equals m times v final. Well, if v final is 0, then P final is 0. So he's going to end up with no momentum. So now we're looking at J, which is his change in momentum, which is P final minus P initial. So that's 0 minus negative 720 kilograms meters per second. So impulse J ends up being positive 720 kilograms meters per second. It's a positive number because the impulse he's getting, his change in momentum is upwards. He was going down, he had downwards momentum, and then he had no momentum. So his change in momentum actually ends up being upwards. So that's why it's positive. So yeah, like it says in bold, no matter which surface he lands on, in either case, the lawn or the driveway, his change in momentum is the same. J equals 720 kilograms meters per second. So I made up these numbers. How long will the collisions take in either situation? So if he lands on the lawn, I just, this seems reasonable, but I totally made this number up. It might take 5/100ths of a second from the time when he starts to touch the lawn to when he completely comes to a rest on the lawn. So 0.05 seconds. Versus if he lands on the driveway, he will come to a rest much quicker. It won't be instantaneous. It will take some amount of time, but it will be a shorter amount of time. So 0.01 seconds. So if we figure out, we're going to use our formula for impulse, J equals Ft, to figure out what force is he getting from the lawn. So J equals Ft, J equals F sub lawn times T sub lawn. So plug in your numbers, and if you solve this for F sub lawn, you get 14,400 newtons. So that's the amount of force that the lawn is going to put on him for 0.05 seconds in order to bring him to a rest. To a stop. So that's a fairly big force. That's going to hurt a little bit. You don't want to fall off of a ladder and land on the lawn. It's going to hurt. It is still better, however, than falling off the ladder and landing on the driveway. So if you do the same kind of thing, but this time we're going to plug in the time for the driveway, we're going to get a different number. So J equals Ft, J equals F sub driveway times T sub driveway. Plug in for J, plug in for T sub driveway, and you end up with a force from the driveway equal to 72,000 newtons, which is even more than 14,400 newtons. So he gets a bigger force over a shorter amount of time to cause the same impulse when he lands on the driveway. So that is the difference. That is why you don't want to land on the driveway, because it will give you a bigger force. You won't get a bigger impulse. The impulse will be the same, but you will get a bigger force because you're getting that force for a shorter amount of time. And like it says in bold, smaller forces are better for Clark's health and better for your own health too. Throughout your life, try to avoid having very large forces applied to you because those are the forces that hurt you. So, can you think of other situations where you try to increase the time of a collision in order to minimize the force of that collision? And I came up with a few. So, you bend your knees when you land. If you were to jump, even from a very low height, or even if you just jump off the ground and, jump up and come back down, when you land, you instinctively bend your knees. You don't want to land with your knees locked and, your legs rigid and straight because that's going to put a very big amount of force, a very painful jolt up through your legs, and you can really hurt your knees by doing that. You also wear protective gear in sports. So shin pads, chest protectors, helmets, all of these things. These things all increase the amount of time that the collision happens over in order to lower the amount of force you get from it. If you have running shoes, your running shoes have nice soft cushioned soles. That's because each time your foot hits the ground, that's a collision. You're getting an impulse from the ground, and you want that impulse to happen over a fairly long amount of time. Because if it happens really quickly, if T is very small, then you get a big force going up from your foot through your ankle, through your shin, through your knees, and through all of the you know, various bones and body parts that runners tend to hurt through repeated use. Um, so yeah, running shoes have cushioned soles. You catch an egg gently. So if you've ever played the egg toss game at like a field day or something, when someone throws you the egg, you reach out and you start to catch it, and while you're catching it, you're bringing it back towards your body. So that's what I mean by gently. You're trying to make that collision last longer in order for the force to be smaller. And then cars have airbags and cars have crumple zones. Both of these things are designed to make the length of time, it all comes back to this equation again, J equals FT. If you're in a car crash and you're going to switch from having some momentum to having no momentum, you're going to have a certain amount of impulse J. If you can make the length of time of that car crash last a little bit longer, that is going to lower the amount of force that you're going to experience in that car crash. And that is why you want those. That is what you want. You want small forces applied to you. So, yeah, that is the idea behind airbags and crumple zones, which, we talked about in class. I'm not going to belabor this point too much there. So, that's the slides. That's part two of the slides. And hopefully you found that helpful.